Good evening. Welcome to the course of electrical engineering. And in this course, I would like to share something about power system evolution. Power system evolution. And in this, I am going to discuss about how our power system gets its name and what are the different stages in the power system. Now I would like to discuss. In that, the first one is the power generation. The power generation. So power generation means the electric power which we are using at different places, either it may be at industries or it may be at domestic level, so will be generated from different power generating stations. Example, from thermal power station, from nuclear power station, from hydroelectric power station, or from renewable sources like from solar energy, wind energy, and many renewable energy sources. And all these power that we are generating from all these generating stations, together I am calling it as power generation. Power generation. And thereafter, power transmission. Power transmission. After power generation, the total amount of electric power generated from all different power generating stations will be transmitted using power transmission lines, and that is what power transmission. And coming to third one, power distribution. Power distribution. Here, the all amount of power that is generated from different power generating stations will be distributed to several consumption points. Consumption points in the sense where the actual electrical energy will be utilized, and those points are, for example, domestic usage, industrial usage, so commercial usage. Likewise, many consumption points are there where the power distribution takes place. Now let me show all the three stages of power system evolution using a flow diagram. So let me take a generating station. A generating station where the power is to be generated, and this power generating station may consist of several number of generators, alternating current generators. They are running in parallel, running at same speed, generating power at same voltage, and all are said to be synchronized. And now the power that is coming out from the power generating station and the power that we are generating at the generating station will be at low voltage. At low voltage, we are generating power, electric power, at all generating stations at low voltage only, and that low voltage is about hardly 33 kV. Hardly 33 kV. Why? Because if you want to generate power beyond this 33 kV, it is possible, but the insulation requirement of the conductor will be very huge, and it is uneconomical, so that we don't go the power generation beyond 33 kV, and it is not advisable to generate electric power at generating stations beyond this voltage because of insulation problem. So now whatever be the power that we are generating at generating stations at low voltage will not be directly transmitted to the power transmission network. And here at the generating station itself, we are having a step up transformer, which can step up the power which we are generating at this station at low voltage to very high voltage, and that high voltage may be 400 kV or even more, 765 kV also. So presently in our country we are transmitting electric power at this voltage. This is the highest transmission voltage in India, 765 kV, and we can step up from 33 kV to 765 kV from generating station itself, or if not possible, we can step up to this voltage at power grid itself, and whatever be the power that is stepped up to either 400 kV or directly to 765 kV will be transmitted through long power transmission networks. And up to this area is power generation, where actual power generation takes place. This is power generation area, and from this the power transmission starts. So now it is not advisable, it is not economical to transmit power at low voltage. Why? Because due to huge amount of line loss, we don't want to go the power transmission at low voltage. We always opt for power transmission at high voltage, at very high voltage. Why? Because let me take an example. A power station which is generating power, for example, say 100 watt. Watt generation is there, and we are generating this 100 watt of power at say voltage. This is power P. So voltage say 10 volt. So the amount of current that we can supply through the transmission line will be, it is 10 amp. It is 10 amp. And this 10 amp of current creates a power loss. Let's suppose line resistance as R equal to say 1 ohm. 1 ohm. Line loss will be it is 100. Total amount of power will be dissipated in the line itself due to this line resistance and due to huge amount of current at low voltage. And the same, if you go for high voltage, say voltage as 50 volts, then the current will be it is only 2 amp. Now the power loss will be or line loss will be same I square R. Now this time current is 2 amp, so only 4 watt of loss. So this is the amount of loss with higher voltage, and this is the loss with low voltage. So that is why we always opt for higher voltage transmission, because the line loss will be less. So now that is why the power that is generated at generating stations at low voltage will be transmitted, will be stepped up to high voltage, and this high voltage power will be transmitted through transmission lines, and all the power that we can generate from the generating station will be transmitted to a power grid. Where so we can have stepping down of power takes place. So power grid is a point where collection of all the power from all different power generating stations takes place, and from that point, from that power grid point, so we can transmit the amount of power required by the load at different voltages. So now This is power transmission network, and we call this as a primary transmission. Just after generating stage ends the primary transmission, and from this primary transmission the high voltage power will be stepped down to reasonable voltage levels. Let's suppose this is high voltage power will be stepped down to reasonable voltages. For example, this is at 765 kV. Now I would like to step down this voltage to say 220 kV. So I'll use a step down transformer here. And the reason behind stepping down that voltage from very high value 765 to 220 kV is, so no industry or no domestic consumer or no commercial consumer willing to take power at this very high voltage because of huge insulation problem. If you want to tap power at this high voltage, you need much amount of insulation. You can't even afford that at a consumer point. So that is why the power that is transmitted at high voltage should be stepped down to reasonable voltage that you can handle at the consumer point. And from this point the secondary transmission starts. This is secondary transmission. And few industries will take power at this voltage at 220 kV. And even lower voltages, if you want to go, then you need to step down the power again from 220 kV to reasonably low voltages, say 132 kV, 66 kV, like that. So again you need a step down transformer. So this is a step down transformer again, which can step down the voltage to 220 kV to say 132 kV. And we can have industrial consumers who can take power at this voltage, say 132 kV. And these consumers are, example I am telling, steel manufacturing industry, and fertilizers, etc. These consumers will take power at this voltage, say 132 kV. Thereafter, again the 132 kV, the power at 132 kV should be stepped down to certain low voltages. So you need another step down transformer here. So here it is 132 kV to, let's suppose, a 33 kV. 33 kV, or you can have 66 kV also. So depends on the consumer point of view. Generally, so from 132 kV to directly 33 kV, we have a step down transformer, general step down transformers, and 66 kV is customized one. Now from this point onwards, electric power distribution starts. Up to this point, from primary transmission to secondary transmission, we are having entire power transmission network from here to here, power transmission network, and thereafter from this point onwards we have power distribution, where the power that is generated from all different generating stations will be utilized here, and at this voltage you have many consumer points. So now this is distribution end, and we call this as primary distribution. And all small scale and medium scale industries will take power at this voltage 33 kV or 66 kV. Medium and small scale industries will take power at this 33 kV voltage, and thereafter again the power should be stepped down to reasonably low voltage, that is to say 400 volt. It is 33 kV. It is say 400 volt. So where actual secondary distribution starts. And all domestic consumers will take power at this voltage if it is 3 phase, and if it is single phase at 230 volt. And from this you have secondary distribution starts, and all other transformers from generating station to this primary distribution, we all have power transformers. All are power transformers. But here at the secondary distribution level, we will have a distribution transformer. Also called as DTR, distribution transformer. And from this point onwards, we have all domestic consumers will be connected. Domestic consumers for apartments, floor mills, shopping malls, etc. All the loads will be connected at this section, secondary distribution section. So here if you observe, at the power generating station we are having low voltage, and at the power secondary distribution level we are having very low voltage, and in between these generating station to the distribution station we are having very high voltage, because to reduce the line loss, so we are going for very high voltages, say 765 kV. This is India's highest transmission voltage till now. Highest transmission voltage 765 kV. And this is how our power system evolution takes place, all the way from generation to the transmission and finally to the distribution. Thank you.